Now, welcome to another Lightblade Learning Lab. Today we're going to do something a little bit different. Now, just recently I detected some rather strange performance characteristics in my 60 watt tube. I call them strange. They're strange to me. For most, in inverted commas, normal people, people that use the machine for daily production, there would not be an issue at all. But because I'm using it for test work and for experimentation, as well as a little bit of work, I was finding some inconsistency, which meant that I couldn't demonstrate some of the things that I wanted to demonstrate to you easily. And so consequently, I had a few words with Thinklaser, and they sent an engineer down who looked at the problem and decided, yep, it was worthy of changing the tube. So, under warranty, without any questions at all, I have a new tube. Now, the new tube is not in there, it's in a box over there, and I've got to fit it. That was my choice, because I felt that if I fitted that tube, it would give me an opportunity to show you how easy it is to actually fit your own tube. What I'm just about to say might sound like a bitch, but it's not. Thinklaser have supplied in this machine, a 60 watt machine, one of the cheapest EFR tubes you can get. Now, as I said, that might sound like a bitch, but in fact, in a strange sort of way, it's a bit of praise. Because, first of all, they've chosen a very good quality tube, EFR, and EFR manufacture 3 ranges of tubes. They manufacture the CL range, which is, I suppose it could be called the basic range, which is something that's been around for many years. And its design has gently evolved, and it's still called the CL range. Now, that's got a supposed life of 3,000 hours. They specify in here, and I'll read the words, working life, 3,000 hours. Now, 3,000 hours is only 4 months. 4 months? No. It turns out, from the information that I get back from Thinklaser, that they've been told from their contacts in China that this working life actually means shelf life. Like most things that come out of China, cynically he said, we don't necessarily believe these numbers. Usually, if it says 3,000 hours, it means 2 hours 50 minutes. In this particular instance, I think 3,000 hours is a gross underestimate. First of all, I've already had this tube in here for more than 6 months. So, first of all, that number's bombed out the water. I've got a machine over there which has got a tube life of supposedly 4,000 hours when I bought it. I've had it now in there for about 14 months, which is over 10,000 hours. So it's already gone 2.5 times its projected shelf life. So we can't really attach a great deal of credence to these working hours life, because that working hours implies beam on, and yet the information that I get implies its shelf life. Who knows? All I can say is that lots of people have got evidence that tells us that these numbers are way, way low if it's shelf life. Now, as well as the CL range, the next range that was developed by EFR was an F series. And the F series has supposedly got a working life up to 6,000 hours. Now, although they give a working life of 6,000 hours, just like Recce or Ressi, you say tomatoes, I say tomatoes, both these very large reputable companies use rather weasel words when it comes to warranty on these tubes. I mean, this 6,000 hours, which is 8 months, has got a warranty of 300 days, but that's about right. But the first 150 days from exit works date on the label, they do a free of charge replacement if there's a problem, but there's all sorts of riders attached to that. And then from the 151st day to the 300th day, there's another set of conditions. So basically, the warranty promises that you get with these tubes are, to say the least, vague. The fact that Thinklaser came in and just immediately said, we're going to replace that under warranty, probably didn't mean that they were going to replace it under the tube warranty, but under their warranty, which is great news. Now, there is another series, which is called the ZS series, which is claimed to have a 10,000 hour working life. Now, there are also additional benefits to this tube as well as its working life, supposedly, but in essence, what it amounts to is, and I've got some prices and prices down here, if you buy them directly from China, for example, this ZS tube cost $275. That's the best price I could find, but then again it was $390 shipped, and then in addition to that you'd have to pay tax of some sort when it arrived in your country. So, you know, at the end of the day, that's virtually $600 plus tax for a top-of-the-range 10,000 hour tube. The middle-of-the-range tube, the best I could find, was, including shipping, it was $175 plus $331, which again is about nearly $500. So it's $600 for a 10,000 hour, $500 for a 6,000 hour, and here we've got something like about $300 total, including shipping, for a 3,000 hour tube. Now, at the end of the day, 3,000 hours, as we said, is rubbish. It's substantially more than that. And to be honest, I believe that Thinklaser have actually made the most economic choice by putting this bottom of the range tube in. Look, whether it's a Mini, a Ford or a Ferrari, 60 miles an hour is 60 miles an hour. There is no difference in performance, only how quickly you get there and the luxury with which you do it. The one thing that really can't change with a machine like this is 60 watts. So I've been supplied with a bottom of the range tube, which I believe is the most economical and the best tube for this machine. And I suspect that this tube is going to last me anything from 18 months to 2 years, which nobody's going to complain about that. Bearing in mind, Thinklaser don't have years and years of experience with these tubes. It's very much hearsay. They are taking this bit at face value, and what they're saying is that at the end of their 1 year warranty, they will supply you with a brand new tube. Now that's a fantastic offer, but it does mean to say that either you've got to pay them to fit it, or you fit it yourself. And that's what I'm going to show you today, how you fit it yourself, because it is a very, very simple task. Now I've already taken the protective cover off here, as you can see, and now I've opened the lid. And you can clearly see what it says on the end of this tube, danger. It's 25,000 volts or more at that end there. Now, if you've recently been running your machine or had it powered on, I earnestly advise you to turn the machine off and leave it. Walk away for an hour, because there's possibly still some dangerous voltages stored in capacitors and various other things in the power supply. Now, I don't know, and I can't be absolutely sure because I'm not an electronics expert or an electrician, but it's a general safety precaution to let any high voltage leak away. Now, do not disconnect your machine from the power supply while you're doing that, because it probably needs to leak away to earth somewhere. If you disconnect it from earth, it might not leak away. So only when you get to the point where you're going to mess around with this should we disconnect the machine. Now down at the bottom there, it's clearly marked with a 220 volt input. Disconnect that plug. And now you know the machine is completely safe. So before you start, you need to disconnect the tube from the machine. Now, I've done that by brutally snipping the cables, because the connector that was in there I couldn't really replace. So I've got several options. One of them is very easy and straightforward. The second one is a practical solution for most people, because they won't have these things to hand. Now these things happen to be crimp connectors. and they will allow me to join two pieces of wire together inside that insulated sleeve, which is fantastic. But you might not have the ability to do that, so what we're going to do is show you possibly an alternative way, and the alternative way is to use one of those. Now I'm going to destroy this because I'm going to cut one piece off, and then very carefully, without cutting my fingers off, I'm going to slice the back off like that. Okay, now with a screwdriver I should be able to push that metal connector out. Now that's got two screws on it, which will enable me to join the wires together, because most people have got these little connector blocks somewhere in their workshop. So that's stage one preparation. There is another important stage that you need, and that's to get some sellotape or some masking tape. Now stage two is to unclamp the tube. So take the clamp screw out. It may or may not come out, but don't lose the screw. And this flexi clamp lifts up a long way. The tube is completely free, except that the water pipes are still connected. But there's a good reason for that, and that is the fact that we've got water in this tube here. Now before we start the next stage, we need again to prepare. We've got a little bucket here, a nice clean plastic bucket, and we need to stand that underneath this return pipe here. There's a possibility that we're going to get a bit of leakage out of here when we take this pipe off, or at least when we start emptying this tube. Well, I'm now going to follow this pipe here, and this is the water outlet pipe, and it comes all the way down here, and there's a label on here that says water outlet. So follow this water outlet pipe back to the chiller, and now we're going to remove this pipe from the chiller. But before the pipe comes off, make sure you clamp the pipe tight. And there we go, we don't have any loss at the moment, but keep that bucket under there, because it is likely that when I keep it clamped, now I'm up in the air, I can undo it and let go of the clamping. And this is where I need the sticky tape, because I'm going to have to put this pipe up here, and that makes sure that the water can't run uphill. Okay, now I'm going to take it off for a moment, because the next trick is to actually blow in it. And what we're going to do, we're going to blow the water back along here and down into the reservoir. And that's when we might get an overflow. There we go. You can probably hear the water flowing. Now, because that's a sealed bottle down there, I suspect that what's happening as I'm blowing, I'm actually blowing some more water up here. But at the moment, the tube is virtually empty. So I got rid of the water out of the tube, and now I can stick my tube up here so that it doesn't leak anywhere. And we should be able to now remove. There is just a little bit of water in there, but it's not going to cause us a problem. I'll now take that one up as well. I'm going to connect this end back down onto the chiller now, because it is empty. And I'm now going to remove this one from here, and just in case, I'm going to take that one up there as well. As you can see here, we have one more cable that's connected, and that's this cathode cable from the cathode end of this tube. So let me disconnect that. Just a tie wrap there. and probably a crimp connector underneath there as well. Now this end doesn't have any high voltage on it at all. This is completely low voltage, this end, and we've got a bullet connector on there which is perfectly okay. But if you don't have a bullet connector, in other words, once you've broken that, you might not be able to replace that. Again, what you can do, we can use one of these connectors, a screw connector. And that's what I'll do inside that piece of insulated sleeve. So now that I've disconnected that black wire, the tube is completely free. And we should be able to lift it out. Okay. Now I'm just going to put a piece of white paper behind this tube because I want to show you something. Now, starting with the most expensive tube, one of the things that they claim on here is long lifespan catalyst coated discharge tube. Okay, now that's normally something you only find in the long life tubes. So let's go back to the 6000 hour, and here it says long life, the catalyst coating on discharge tube. That's the key thing, a catalyst coating. And so when we get to the cheap tube, the 80 watt tube, catalyst doesn't say yes, doesn't say no. With the 1200 CL tube, which is the one that we've got here, it clearly says catalyst yes. And I can see that. Can you see that pink tube in the middle there? The fact that it's pink tells me that it's been flash coated on the inside with gold. And that gold flashing is an indicative feature of a long life tube. It helps to recombine any free oxygen with the carbon monoxide to keep the CO2 up to a reasonable level. It delays the death of this tube. And so this is a hallmark of a very, very good tube. Now, you won't find that catalytic tube in most economy tubes, should we call them. Okay, now sadly the first thing I see is I've got to be a bit brutal with this tube because it's got a very, very nice connector on it, which is a proper high voltage connector. But I don't have the mating female connector that goes on the other side of it. So I'm going to have to cut that off there and make the connection as per we discussed. So obviously this red end, the red cable, the high voltage cable, goes to this end because that's the way that we took it out. This cable here needs to come down. Oh, they've already supplied me with a little connector there, which is great. They've already supplied me with a bullet connector. Oh, that's good news. So I haven't got to fiddle with that end. So I said there's absolutely no reason why this needs to be fully protected, this end. There's no voltage here at all. And current, well, current is very minimal. It's only somewhere in the region of around about 22 to 25 milliamps. So we can lose that back inside there, and that's that end made off. We've got a fair amount of tube here, and that's good because what I want to do is to nick something like about 2 or 3 inches of that tube. And we'll plug that back on there, and we turn it so that it sits at 12 o'clock, and we'll push it back as far as it can go because I need a reasonable gap here to do my tests. So somewhere in the region of about 40 millimeters I'm going to leave here. I will try and just take the end off of it with a cable of the cutter. And as you can see, there's a plastic coating inside. It's double thickness. Now I don't think I should be able to get that layer off because it's bonded on to the cable inside. Because it's not taking a huge amount of current, it's just taking a huge voltage. So that's one end. Now, as I said, sad to say, I've got to be brutal with this end. So I've got a nice tight screw clamp connection on there. So just to be doubly sure before I put that over a high voltage connection. There we go, that's cleaned it out nicely. Now I'm going to pop that on there, like that, before I connect this side up. And there we are, a nice positive connection. It's only got to carry a few milliamps, as I said. The problem is trying to keep the very high voltage electricity away from the air. Because if there's any dampness in the air, effectively what we've got is the potential for lightning between here and the chassis, somewhere ground. And so what we have to do is make sure that we completely isolate it. That's why I'm using this thick silicon tube. It makes a fantastic insulator, and we can slide that inside the tube like that. And what I've got here, and you can buy this from places like Maplin. Now this is a white silicon sealant and adhesive. It's not bath sealant. Whatever you do, don't use bath silicon, because bath silicon has got chemicals in it which you can smell and it will corrode the joint in there. So you need to go and get non-corrosive silicon. Right, there we go. We'll put some in that end like that. Now, as you can see, that is very nicely sealed off round this cable and the inside of the tube, so there's no chance of any air getting in there. It'll probably take half an hour to an hour to dry. Now, I put the cable tie on the other end because I thought it was going to run right the way through, but it hasn't. It's horrible stuff if you get it on your hands. And there we go, we'll put a cable tie back on this end as well. So there we go, look, I've just wrapped that around here, and this is sitting right in fresh air, so there's no chance of any discharge to anywhere, and I've just tie wrapped it against itself. So we can put this water pipe on here at the end. There's only one place to put it because there's only one connection free. So we will just check that we've got clearance on the end of our tube when I put the case on. So we'll just put the case on, just test the case on there. And yes, it looks as though we've got about 3/4 of an inch to an inch clearance, which is fine. We've got our cathode connected, we've got our anode connected, we've got our water outlet connected, and we've got our water inlet connected. We're basically done. I've set this gap here to about 40 millimeters, which is what I need, but if you want to set it closer, you can do. So now we'll just clamp the tube back up. Now, because these tube clamps have not been moved, basically I would expect the tube to be fairly well aligned. It might need a tweak, the beam alignment, but that's all, just a tweak. And that's it, the tube is fitted. It's no more complicated than that. 4 wires and 2 water pipes and a little bit of care about how you connect it up. It's the method rather than the difficulty. One final little job to do. So I'll just cut the bottom off of an old water bottle and made myself a temporary funnel. Otherwise this could be a little bit of a messy job. Job done. And that's the final little task. So we'll leave it for a few hours now just to let the sealant settle around the HV connection, and then we can give it a try. Well, we should plug the power back in now and we'll turn the machine on. So we're going to have to make sure the tube fills up with water to start with. Here comes the water through the tube, and it's cleared the bubbles absolutely perfectly. So the first thing I'm going to do is set max power, make sure it's about 25%, which it's not at the moment, it's 70%. And now I'm going to press the pulse button and we're just going to check what happens. There we go, look, we've got a beam. Very nice. Okay. Now in the past I've used these target holders that we've made to sit on the mirrors and the targets. But if you happen to be unlucky enough to have a machine and you haven't made these, then you can't use that sort of target. So what I've got here is a slightly different approach, which maybe even Thinklaser can supply with a new tube, and that's these little targets here. So we pull one target off and we'll go around to mirror one. And what we're going to do is we're going to pop this into the mirror orifice, and I'm just going to hold it in place with a little piece of tape across the top like that. Now I'm going to turn the power down to 15%. So I would say it looks as though that beam has got to go up by about 2 millimeters. Now, how do I get the beam up by 2 millimeters? I want to lift both ends of the tube up by the same amount, i.e. 2 millimeters. We've got these screws on here, and underneath here we've got like a locking collar. Now, that locking collar can lift up and down. It's an adjusting collar. Twist it down so that it sits on the top of the pillar. So I happen to have a piece of perspex here which is 2 millimeters thick, and what I'm going to do now is that once this collar is sitting down on the top of this pillar, and I'll make sure that the one at this end is the same, I'm going to undo these two screws here, which will allow me to lift the beam up. And I'll put that spacer underneath there, and I will lock the screws back up. And I'll do the same at this end. Undo the screws. Lift it up by 2 millimeters and reclamp it. And now it's gone too high, so it probably only wanted to go up by 1 millimeter. Okay, well, I've got a piece of 1.1 millimeter thick material, so I can undo the screws again and let it drop down onto that piece of material and tighten up the screws. Well, that looks to be pretty well spot on, so let's just run it once more. And that's not looking bad at all. Okay, so we've driven mirror 2 right to the front edge of the machine. We'll put a target into mirror 2. Well, we can see that it's quite a long way out on mirror 2. Height is not bad. This mark is what I call a sighting mark. So what I'm going to do is to tip mirror 1 very slightly. Okay, now that's not far out. It does not have to be perfect. It has to be more or less on centre. But, you know, 1 millimeter either way is not a problem. We'll replace that target, and this time we'll bring the head right to the back of the machine. This burn is what I call a target burn. Okay, now that's our marker. It's actually not bad. Move back to the front of the machine. And now what we've got to do is we've got to make a mark that matches that one. We've got to adjust the mirror so that the two marks are coincident. As you can see, it's very slightly to the right. So I need to take a little bit off that mirror. Too much. Now that looks pretty good. Now, not only do they line up with each other, they're also more or less on centre. Now it means that the beam is actually lined up with this y-axis in both the horizontal and the vertical plane. Now we've got to get the beam onto the centre of mirror 3. So we will first of all go for our sighting. There is another size in here which is a slightly different size target which we shall need to use for this particular situation. Now we shall definitely need a small piece of tape on this one because there is nothing behind it. There's no mirror behind here to hold it. So what we're going to do is we're just going to drop that into the hole. Okay, so I've now got the head pushed as far away from mirror 2 as I can get it, and we'll do a sighting pulse. Well, it's not terrible, but it's not brilliant, but not to worry at the moment, because what we're going to do is we're going to do a target pulse. And so here we are, right up against mirror 3. And that's our target pulse. Sighting pulse, target pulse, and then alignment is the procedure that you should go through for each one of these axes. So that's our target pulse. Let's see where we are. Well, I would say we're possibly just about 0.5 millimetre high. So we need to just drop that very, very slightly. And I've just tweaked that mirror. And I would say that that's probably just about spot on. And this is where people can get very confused, and why I personally believe that these machines are not really designed to make it easy for beam setting. I personally think that mirror number 2 should be a static mirror, and then this one should be an adjustable mirror, because what we want to do now is to move that head to catch the beam on that centre. We can't adjust the mirror anymore because we've already got the mirror set up so that the beam is running horizontally and vertically true to this X. But of course, as soon as I twist that mirror through 45 degrees, look what happens to it. It shrinks, its height changes, and it's no longer 23 millimeters tall. It's probably only about 13 or 12 millimeters tall. We've got to be very accurate with the alignment of our beam in this up and down vertical axis. How are we going to get that beam down? Well, we could go right the way back to the laser tube and drop it down, but hey, we just raised it by 2 millimeters to get it central on the other mirrors. Well, the other mirrors are twisted this way, so they are a lot less sensitive in the height position than mirror number 3. So I've got two choices. There are some adjusting screws on here which will allow me to adjust it this way by a small amount, which I could certainly use to get this in, but I've got no adjustment up and down on this head other than to put some packing pieces underneath there. In other words, I could shim the head up. A possibility, but a bit of an ugly solution. So what I'm going to do is go right the way back to the back and drop the beam down by the millimetre that I lifted it up. Fortunately, I left the collars set, So it's only a matter of loosening those screws and dropping it down onto the collar, tightening the screw up and doing the same at this end. And let's see what effect that's had on the position of that beam. Hopefully the beam should have dropped down a millimetre. And there it is. And that's back to spot on. Now what it does mean is that the other mirrors are very slightly compromised. Because those mirrors are twisted this way, I've got to be accurate in the horizontal plane, less so in the vertical plane. So it isn't a big issue. This one is absolutely essential. Now it is very, very slightly, maybe half a millimetre out of position in this direction. But again, because this mirror is tipped this way, I can afford to be very slightly out in this horizontal direction. And so I'm not going to go hunting any further for the problem at mirror 3. That's as good as I can get. Okay, now we're into the final stage of setting this beam up, which is trying to make sure it comes down here vertically to get to the lens. Now to do that, I'm going to remove the air assist and we're going to remove the lens tube itself. Now I'm going to set that target on there and I'm going to raise the table. Not too much. And I'm going to guess roughly where the centre is. It doesn't matter too much. Let's just show you what I mean. I know it's not on centre, but that doesn't matter, because what I'm going to do is to drop the table down by about 2 inches. So this is the same 3-step approach that we used for the mirrors. This is our target pulse. Well, I think you can see that the difference is nil, which means that that beam is coming true right down the centre there, because it hasn't deviated in X or in Y. That's about as far as we can go. The beam lines up with everything as we require it. Now we haven't had to do a great deal, but the one thing I just reinforced to you again is the 3-step principle that I use. It's taken half an hour because I'm showing you what I'm doing. It would probably normally take me no more than about 5, at the most 10 minutes to fiddle around with this. 3 simple steps, remember? Move things as far away as you possibly can and get a burn so that it's approximately in the area where you want it. That's what I call the sighting burn. Then we move this mirror close to the other mirror that we're trying to set up, and we then do a target burn. Then we move it back far away and we align the mirror onto the target burn. Those are the 3 simple steps. Once you've done step 1, 2 and 3, you only need to keep repeating steps 2 and 3, 2 and 3, and you shouldn't have to do that more than about once or twice, and you should have the beam perfectly aligned with the axis that you're working on. Okay, let's put this back together now. We can now use our, what I endearingly called the laser thermometer. This is the final test because we don't want the beam to clip the edge of that orifice, otherwise we should be losing power. And it does look as though the beam is sitting down here at about 6 o'clock. So we could really do with trying to tweak that beam up to a slightly different position. Now we know that they're all in the same position, so we don't have to go around and check every other position. We don't have to check all the positions again. So all we need to do is just check it in one position. And there we go, dead centre. So that's the final check to make sure that the beam is not clipping the nozzle. It's got to be in the centre of that target, give or take about 0.2 or 0.3 of a millimetre. Now, unless you have a big block of perspex like this, you won't be able to carry out this final test. But this is something I like to do. I'm going to put this right towards the edge. I'm holding the pulse button on. Okay, so that's the beam going down in relation to a set square. I think you'll see that it's pretty well upright. And then if I check it in the other direction, it's not too bad either. Well, I can remember the feelings that I had the very first time I started fiddling with my mirrors. Was I ever going to get the machine back into working order again? I hope today's session has done two things for you. One, it's given you sufficient confidence that you will be able to dive in and change your own tube. And if as a result of that you find that you need to adjust your mirrors to get the beam back into good alignment, then I hope I've taken the mystery out of that for you. Now, this very simple three-step procedure for each axis, as I've explained it to you, is a foolproof method. It will work every time. But you have to think about whether you're going to move the source of the beam or catch the beam. Today, I think I demonstrated that it would be good and simple to catch the beam. But we've come up with a compromise which works perfectly well on this machine. And I'm now very happy that this machine is completely set up. Now that we've got the machine back into good working order, in the next session what I need to do is to establish just how good that new tube is. So we need a record of its performance today, brand new. I'll be going through that process in the next session. So, until the next time, thanks for your attention.